Okay, welcome. So what we're going to be going over today is sort of an app the what I think is the primary application of the concept of momentum, and that is going to be the conservation of momentum and then sort of how that applies. Okay. So last time we went over the ideas of impulse and momentum. This time we're going to be fleshing that out a bit more and really just focusing on momentum this time. Okay. Now, the idea here is, as a reminder, what we had last time, and I used the symbol J for impulse. I'll just do that for shorthand. Like I said, the book doesn't do this, but that's fine. J equals delta P. And as a reminder, J was equal to, and I'll put the net there. So J net was equal to F net delta P. Um, and so the idea is that if F net equals 0, then J net equals 0, and then delta P equals 0. So this is basically the statement of conservation of momentum. If F net equals 0, delta P equals 0. And you might say, isn't that just first law? And you'd be correct. This is a certain way of stating first law. However, this is very, very useful if instead of thinking about particular objects, we think about systems of objects. So I'll capitalize this: very useful for systems of multiple objects. Okay. Now, why is that? Well, the idea here is, remember that if two objects bump into each other, then multiple objects, then they exert a force on one another, right? Like two balls hit each other in midair, then they exert a force on each other, they change each other's motion, so on and so forth. But the point is, if we consider those balls as a single system, if we consider it as a single system, then what we can say is we can say, okay, if we're going to consider them as a single system, then basically then there was no force. Their third law pair forces canceled each other out, which means that the total momentum, the total change in momentum of that system should be 0. Now, basically, you have one ball going this way. Its momentum is, however you're saying that. For me, it's to the right. The other ball, its momentum is to the left. If they strike each other and fall to the ground, then basically what happened is their two momenta canceled each other out. But the total momentum was the same before and after the collision, because direction is relevant. So a momentum to the right cancels out a momentum to the left, or it can partially cancel it out. And that's a big part of what we're going to be doing here. Okay. So the idea here is that when we have collisions. This is the main thing that we're going to be looking at with conservation of momentum. And basically what we have is we have two objects with their own initial momenta, I should say, and they are separate. They're not the same. They're two separately traveling objects, so separate objects. They collide, and we could say that they exert a force on one another. On one another. But the idea is that that force that one object exerts on the other, those are third law pair forces. Third law pair forces, which means that they will cancel out. They cancel out if viewing the two objects as a combined system. Okay. So thinking back to when we talked about third law, basically what we said, if you were pushing on one block and that block was then pushing up against another block, we said basically what we can do is we can treat those two objects like one system. And then we ignore that interaction force that's occurring at the boundary of the two boxes because it's just a third law pair and they cancel each other out. Okay, so if you group the two objects into one system, then you don't need to worry about how their interactions, about how their interacting forces impact things. You don't really even need to take them into account. And the idea is that so this means for a collision, F net equals 0 if all objects in the collision are included. Okay. And that's just because if you include all those objects in your system, then all their third law pairs cancel each other out. If you don't include one of the objects, then you have to worry about the forces because then the third law pair is not included in the system. So that's the idea. Now, what does this mean? Well, according to the conservation of momentum, so the conservation of momentum, if we have F net equals 0, then delta P equals 0. Okay, so basically this is another way of saying P final equals P initial. Okay, and we could do I should definitely have the vectors there because vectors are relevant, and sign is going to be relevant for momentum. Okay, it's not relevant for energy. We didn't care about the direction the thing was moving, but for momentum, sign is going to be very important. The direction is something we're going to have to take into account. Okay, so this problem will be similar to one that's on the homework. This first one I want to look at. Whoops, I don't need to do that. Did that. Okay. So just to give you kind of a sense of what I mean with this. All right, so we have train cars are coupled together by being bumped together. Suppose two loaded train cars are moving toward one another, first with a mass of 150,000 kilograms at a velocity of 0.3 meters per second, the second having a mass of 110,000 kilograms at a velocity of negative 1.2 meters per second. The minus indicates direction of motion, okay? So this problem, they're kind of nice about it in that basically what they're saying is if we draw the picture, what we have here, and we can even, set this up correctly. We have M1, and we could just say M1 equals 150,000 kg. And then this thing is going at a velocity of 0.300 meters per second. And then we have M2. And basically, this one is going in the other direction at a velocity of 0.120 meters per second. Now, the negative is included. Like the key thing, and one of the things that some people will struggle with, is that if you're given these type of problems, sometimes they won't give you the negative. They'll just tell you to the left and to the right, and then you need to know that direction is relevant. And one of those needs to be positive and the other one needs to be negative. Okay, so that is the idea. So when we set this up, I would say, okay, M1 equals 150,000 kilograms. V1 equals 0.300 meters per second. M2, I didn't put that, but M2 equals 110,000 kg. So M2 equals 110,000 kg, and then it looks like a 6. A couple of those look like 6s. And then V2, we would have to make sure we do include the negative 0.120 meters per second. Okay, now why? Well, basically what we're going to do is we're going to do a before collision and an after collision, okay? And we're basically going to calculate the initial momentum of both of the cars. So we need the initial momentum of car 1, the initial momentum of car 2, and then the initial momentum of car the final momentum of car 1 and the final momentum of car 2. Okay. Now, this is going to be we're going to have to realize kind of what's going on here. After is going to be a little bit tricky, but with before, what we can do is we can just calculate this directly. So it would be 150,000 times 0.3. That would be 45,000, I believe. Yeah, 45,000 kilogram meters per second. Now, this next 110,000 times 0.12, I think that would be, I feel like that is like 13,200, but I need to check it because it's negative too. So 0.12 times 110, yeah, 13,000, negative 13,200. Negative 13,200. Okay. And this is, again, kilogram meters per second. So now what we can do in the before category, we could do the initial total momentum. Okay. And if we're going to analyze the system, we have to combine the momenta of the two colliding objects in order to get the total momentum of our system. All right. We need to include both of these things. So when we do this, we're going to get, it would be what, 44,800 minus 13, which is 31,800. 31,800. And that becomes a positive kilogram meters per second. Okay. Now, basically what we do is we realize that this initial momentum is just equal to the final momentum. Okay. And that is the whole magic of conservation of momentum, is that once you get either the total initial momentum or the total final momentum, you can get it, you have it both before and after. Okay. And that's what's so nice about how this works. Now, when finding the individual things, what we need to realize is that they've effectively become one object. So become one object. And this is a certain type of collision. We'll get to that in a minute. But sometimes when two objects collide, it's actually somewhat common. They collide and they join together. They stick together and become one object. Two train cars coupling would be an example of this. Now, what is the mass of that one object? Well, the mass of that one object, so we would just call this with m equals, and it's just the sum of the two initial masses of the mass of the two trains. So that would be 260,000 kilograms. Okay. And basically what we can do then is we can say, okay, this final momentum is just the mass of the two cars times whatever their final velocity is. So we have 31,800 is equal to, sorry, hold on. There we go. Yeah. Okay. 31,800 is equal to 260,000 kilograms times V final. So V final is then just going to be 31,800 over 260,000. Okay. So when we do that, 260,000, that's going to give you a V final of 0.122 meters per second. Now, it is worth knowing and at least asking yourself when you calculate that, what does that mean? Is it going to the left or going to the right? Now, we know that we defined right as going to, at least as I've drawn this, we defined right as going positive. So if this velocity is positive, then this would be a rightward direction. Okay, so that is what is happening there. All right, so that is just sort of how this goes. Okay, now I want to get into types of collisions because there are some different kinds. of collisions. Now, the first type I want to talk about is elastic collision. Now, we're not going to do very much with this because in order to actually analyze elastic collisions, the math does get kind of the algebra gets difficult, and I don't really want to focus on algebraic tricks. But elastic collisions, these are collisions that occur where kinetic energy is conserved. All right. Now, this is not going to be true for all collisions. Momentum will always be conserved in collisions, but not true for kinetic energy. So, an example of this that you might imagine is if you throw two balls of mud at one another, they both have some amount of positive kinetic energy. They're coming together, coming together, coming together. They collide in midair, and then they just fall straight to the ground. So basically, their momentum offset because it was in opposite directions, but their kinetic energy basically just dissipated in the collision. Once they collided, like all their kinetic energy was removed, and so that was gone. Now, alternatively, is if you had those little rubber bouncy balls and you throw those at each other, what they would do is they'd come together, come together, come together, and they'd bounce off and go back the other way. Okay. And in that case, the momentum was still conserved because basically what would happen is they would just switch directions. But the total momentum would still be conserved. But this time their kinetic energy would also be conserved because they had bounced off and they had retained their speed. Okay. So typically elastic collisions, this occurs between bouncy objects. Now, a question I often get is, okay, but none of these things are like, you never really get kinetic energy to be conserved. In general, that's true. Billiard balls are probably the closest you get in physics, and a lot of times when you have a kinetic energy problem, they'll frame it as a billiard ball problem. But you would be surprised how often this actually works. A lot of collisions at an atomic level are basically elastic. Okay, they're basically elastic. Like there is so little kinetic energy lost in the collision that we basically just treat them as if they're elastic collisions. Okay, so when we're looking at like air molecules bouncing off the side of a container, we basically treat those things as if they're elastic collisions because they don't really lose that much of their speed to the collision. So that's something to keep in mind with that. All right. Now, if there are elastic collisions, then there are inelastic collisions. This is kind of a boring category. This just means kinetic energy is not conserved. So I'll write this. If kinetic energy is conserved, it means that your initial kinetic energy equals your final kinetic energy. For inelastic collisions, kinetic energy is lost. And this is the main thing that comes up with inelastic collisions. A lot of times you want to find K initial and K final. Initial kinetic energy and final kinetic energy. Sometimes you'll be asked to find the loss. So find the loss. This would just be K final minus K initial. Sometimes you're asked to find the percentage loss. So that would be delta kinetic energy. Find percentage loss. This would be actually, sorry, a loss would be K initial minus K final. That would be a change. A change would be K final minus K initial. You generally don't gain energy in collisions. Sometimes you can, but that energy needs to come from somewhere. What can happen there is if like you had two things collide and you had a loaded like a compressed spring, and when they collided, the spring was set loose. They might bounce apart with even more energy than they had before. But turns out momentum would still be conserved in that case. Which is kind of cool. So if you wanted to find the percentage loss, that would be your change in kinetic energy generally represented as a positive number because you're talking about percentage lost over the initial kinetic energy. So those are some of the questions that can come up with inelastic collisions. And then there are perfectly inelastic collisions, and that was like the perfectly inelastic collision. And basically a perfectly inelastic collision. This is the one we did with the train. This is the two objects joined together. So that is what we mean by a perfectly inelastic collision. They join together and travel as one. So the two trains joining is a very common one. Another one is if you have two cars, and like I said, we're not really going to get into two-dimensional momentum, but if you had two cars and one of them T-bones the other one, and then they just travel as a single unit for the rest of the collision, that would be another example of a perfectly inelastic collision. So travel as one object. Now, the main thing here to keep in mind is that the final mass is just equal to the sum of the initial two masses, and they have only one final velocity. So there is only one final velocity in this case. So I think the perfectly inelastic collisions are I think are the easier types of problems to do. The hardest ones are definitely the elastic collisions because instead of being given a parameter, you have another equation, which is often difficult to solve. So that's why we're not going to deal with it much. But the perfectly inelastic collisions, I think are worthwhile. Now the other thing to think about with these, not necessarily think about, just other thing to know, is that in perfectly inelastic collisions, this is the case of maximal loss of kinetic energy. Now, sometimes that means that the two things will remain stationary, but not always, okay? It's far, far more like the way you can think about it is in a collision, the conservation of momentum rules first. So momentum absolutely has to be conserved. And when you have two objects colliding, sometimes you can't have them collide and then have neither one be moving afterwards and have momentum be conserved. And the only way that could work is if your initial momentum was zero. So the only way that would work is if their momenta exactly counterbalance one another. So if there's same mass and same speed, or some variance such that the momentum in one direction was exactly offset by the momentum in the other direction, then you could have a collision where they stopped. You wouldn't need to, but you could have a collision where they stopped. If that's not the case, like you could imagine, kind of like we had with the train, where one of them is going faster than the other one and it was more massive, then there's no way that the less massive one is going to stop the bigger one. It's gonna go. Now, maximum kinetic energy will be lost in that case when they join together, but the things did not end up stopped. Okay. So another one you might imagine is you rear end someone, where this person might be stopped or moving forward. You just come up and you hit them faster. That you and if you join together, and you travel as a single object, that doesn't mean that you've stopped. Okay, but it does mean you have lost the maximal amount of kinetic energy that can be lost and still have momentum be conserved. Okay, so those are the three types of collisions that will come up. Like I said, they'll, we'll be looking at this. I wanted to do a couple other examples. There's really only like I said, the elastic collisions are not going to be as important. Okay, so there we go. All right. Okay, so what we have here is oh, wait a minute. I guess, hold on. That's fine. Okay. Yeah. Okay, so a 0.24 kilogram billiard ball is moving at 3.00 meters per second and strikes a bumper and bounces straight back at 2.4 meters per second, 80% of its original speed. The collision lasts 0.150 seconds. Calculate the average force exerted on the ball by the bumper. How much kinetic energy in joules is lost in the collision? What percent of the original energy is left? Okay. This one is interesting because while it's referred to as a collision, the momentum is not going to be conserved in this case. Okay. I want to do this one. This is kind of a joining of the two topics from today and yesterday. Momentum is not going to be conserved here. Okay. And the reason is because it's basically between the pool, the billiard ball and the pool table. And the pool table is basically anchored to the ground, or at least it's held to the ground via friction. So it's not free to move. Okay. So if we can't include the table in our system in order for momentum to be conserved. So that's basically what's going on here. We're not allowed to do that. All right, but we can use our impulse equals delta P equation. Okay. And the way we're going to do this is we can remember that our impulse is going to be F net delta T, and then the delta P. Going P initial, that would just be MV initial. So it'd be 0.24 times 3, which would be what? That's 0.6 plus 1.2, 0.72. 0 kilogram meters per second. Now, for P final, this would be M of V final. Most people will just do 0.24 times 2.4. And you're kind of sort of correct if that's what you thought. But, whoops. 2.4 times 0.24. Yeah. But you got to make sure that you realize it's going in the opposite direction of your initial one. So you can let either one of these be positive, but when the other one is going in the opposite direction, you got to be real careful to make sure that the other one that it indicates it is going in the opposite direction. Okay. So this one would be negative 0.576. All right. Now delta P, we do P final minus P initial equals delta P. So that's 0.576 minus 0.72, which is going to give you, so it'd be negative there. And that's going to give you negative 1.296. Okay. So that'd be negative 1.296. All right. And then your F net. So this would just be F, and this would be of the bumper, because that's the only thing that exerts a force on it during this collision. And then the delta T, which was 0.015. So F bumper is equal to negative 1.296 divided by 0.015. And that will give you a negative 86.4 newtons. Okay. Now, negative, that just means the force is in the same direction as the final velocity, which makes sense. If we had initially going to the right, afterwards going to the left, the force had to be on the left. Like the force had to first stop its velocity to the right and then force it to go the other direction to the left. Okay. So that would be 86.4 newtons. That's how we would find that one. All right. So this would be the average force. And again, when it says average force, as a reminder, the kinematics equation we used was a constant acceleration equation. So we basically have to assume that the average forces generate a roughly constant acceleration. So that's why in a lot of these problems you see average force. It won't be just this force during that time. Like the force will increase as the bumper gets more and more compressed. But for our purposes, we generally just do it like this. Okay, so how much kinetic energy in joules is lost in the collision? This is more of an energy problem, but I did want to, like I say, I did want to bring in some of the inelastic stuff. So our initial kinetic energy, this is 1/2 mv initial squared. So this is 1/2 times 0.24 times 3 squared. So 0.5 times 0.24 times 9. That is equal to 1.08 joules. Our K final, 1/2 times 0.24 times 2.4 squared. And I should probably do negative 2.4, but when you square the negative, it doesn't, nothing changes. So that's fine. Times 0.24 times 0.5. And that would be equal to 0.691 joules. And then you subtract the two. Whoops. 1.08 minus point. That should be joules. It should be joules as well. Looks like a 5. 691. And then you end up with delta K equals 0.389 joules. Okay. So that is the joules, the amount of joules that were lost. To find the percent remaining for part C, that would just be 0.691 over 1.08. So 0.691 divided by 1.08. So that was the initial. And this is going to be about 64%. And the thing is you can kind of get to this. You don't really need to do this calculation because the problem, in fact, tells you that 80% of the original speed. Well, if it's basically you could just say, okay, 80% of the original speed, if I square that, I'm down to 0.64 or 64% of the original kinetic energy because the mass and the 1/2 don't change. So only thing that changed is the speed. If the speed is at 80% of its original, then you've actually lost 64, or you're down to 64% of your original kinetic energy. Okay, so that would be really, it's like the way I calculate it because of the rounding, it ends up being like, whoops. Okay, that's no good. Yeah. Anyway, because of the rounding, it ended up being down to like 0.639. Oh, come on. Okay. But in any event, it ends up being about 64%. Okay. So I think, tell you what, let's do this one as well. Let's do one more. So during an ice show, a skater, 60 kilogram skater, leaps into the air and is caught by an initially stationary skater, 75 kilograms. So I'd start doing these things. I would say M1 equals 60.0, M2 equals 75. V initial 2 is 0, and I know that is initially stationary. That's what I would say that. What is their final velocity, assuming negligible friction, and that the 60 kilogram skater's original velocity is 4.0 meters per second? So V1 initial is 4.00 meters per second. And there we go. So then we want to know how much kinetic energy is lost. I would go ahead and just calculate the initial kinetic energy as well. So I'll do a couple of things. P1 initial is just 60 times 4, which is going to be 240 kilogram meters per second. K1 initial is going to be 1/2 times 60 times 16. So it would be 60 times 8, which would be 480 joules. Okay, so that's cool. Now the P2 initial is going to be 0 because velocity is 0, and K2 initial is also going to be 0 because velocity is 0. Now what we can do is set up a before and an after. All right. Now, after, as a reminder, they're basically one object. So this is a perfectly inelastic collision because the second one caught the first one. So the mass, the new mass of that object is 60 plus 75, which would be 135 kilograms. The V final is what we're looking for. And then we're also going to be looking for the K final. So V final and then K final is also going to be what we're looking for. Now, the P final, well, that's basically going to be our avenue to find V final and then ultimately K final. Okay. So what we do is we do P1 initial, and we already found that it was 240. P2 initial, well, that one was just 0. Okay. So our P initial is just P1 initial plus P2 initial. We're just adding the two momentum of the two different objects, which is just 240 because it's 240 plus 0. And then that goes to the P final. Okay. So that is 240. And now if we want to find the V final, as a reminder, P final is equal to M, and this we could even put an M final there because it's a single object. M final times V final. And that would mean V final is equal to 240 over 135 once we solve for that. So find that out. And you get 1.78 meters per second. And then we can find the kinetic energy, the K final. So we'd take that velocity and we'd square it. And then we'd multiply by the 135 because that's the mass, and then we multiply by 0.5, and we find that our K final is equal to 213 joules. So how much kinetic energy is lost? Well, we do 480 minus 213, and it would be 270 minus 3, which would be 267 joules were lost in that collision. Okay. So that is basically what is going to happen with that one. All right, so that is going to be it for this lecture. You should have what you need to do all of the homework problems. Thank you for joining me. I will talk to you next time.